Hello, this is Jack Anthony, and this is my Astro Rant for 3 December 2020, the astrodynamics of the GEO disposal orbit. Basically, what we're going to talk about is when a geosatellite's done with its mission and it's still functional and has some fuel, it needs to boost up and out of the way into what's called a graveyard orbit so it can make room for others. So how high is high enough for this graveyard orbit? There's a few factors that are involved, and we're going to talk about that. The biggest one, I think, that we have to explain to you today is solar radiation pressure, the effect of the solar wind on your satellite. And it's a function of the characteristics of your satellite, okay? So its cross-sectional area, its mass, and its reflectivity, okay? So look at the blue box. You see the sun emanating the rays, and they're coming towards the Earth, and they go zipping by the Earth. But you see that counterclockwise orbit, and what happens is there's part of the orbit where the solar radiation, the wind, is in your face. There's another part called the tailwind where it's pushing you along. Those are like teeny weeny delta V's, the headwind being a retrofire and the tailwind being a little addition of velocity. This is going to change your orbit. Specifically, it's going to change the eccentricity, okay? So I'm going to try to use my marking pen here. First thing we're going to do is talk about the tailwind, the headwind, okay? We'll talk about that right up here, okay? So you see that little yellow arrow? That's the solar wind whizzing by, but you'll see your red orbit is going right into it, okay? That is taking energy out. So what is going to happen is the green orbit is going to happen right here, and it's going to lower its perigee, okay? So that's what the headwind does. All right, let's go down here and look at what happens with the tailwind situation, okay? So here, with the tailwind, it's like you're getting a little boost. You see, the yellow arrows are lined up, and therefore you're getting pushed from behind. What that does is it creates a higher apogee, okay? So what used to be a circular orbit now has a non-zero eccentricity, and we have a situation as we see over here. Let's see if I can get it. Yeah, I got it. Okay, the net effect is the circular orbit is now non-circular. It has the same orbit period, but the eccentricity increased a little. The orbit will now have a perigee below the original orbit and an apogee above the original orbit. It's that lowering, it's that dip of perigee that could be a problem. We have to figure out for our spacecraft how much it's going to dip down, okay? So, I hope this made sense, but as you can see, Snoopy's there getting ready to head to his geosynchronous orbit. Again, it's all about the wind either hindering or helping our progress and creating little mini delta V's to change the orbit. That is, change the eccentricity. Let's go to the next and final chart. Okay, this is the layering or the buffering chart. Okay, let me explain this to you. Okay, I'm going to try to use the marking pen again. And let's see. Okay, hold on. Boom. And boom. Okay, what we have is this thing called the GEO protected zone. The Interagency Debris Coordinating Committee came up with it. Plus or minus 200 kilometers GEO altitude is a protected region. That's where they feel everybody is operationally operating, okay? So they don't want people that are pooped out satellites hanging around in there, okay? Well, the first thing we are going to learn about is the green zone here, okay? Right here, this 35-kilometer thing is a constant. The perturbations due to the Earth's odd shape called geopotential, the moon and the sun tugging on the satellite, causes a circular orbit up in that region to dip their perigee down as much as 35 kilometers. So they add that to the top of the GEO protected zone. So now we're at 235. So that's really neat. A little buffer there, the green buffer. Okay, but now what we're going to do is we're going to look at over here, we're going to look at how we get this solar radiation pressure thing, this factor. Okay, it's an it depends thing. Well, what does it depend on? Well, we happen to have this really nifty equation here to help you understand that. So first, we have this 1000 factor, so that's an easy one. Then we have this thing called the solar radiation pressure coefficient. It's usually between 1.5 and 2. That's how much momentum gets exchanged with your satellite. So the photons are bouncing off you and pushing you around, okay? Then this is the big factor that is highly dependent upon you. You got big solar arrays and stuff facing to the sun. That gives you a large cross-section area. And your mass, once you're up into your disposal orbit, is the mass term. So cross-sectional area over mass. Okay, so you run this calculation for your vehicle and you get this solar radiation pressure distance, this red layer to add. And it can be a pretty big number. In my read ahead, I did some examples with your favorite satellites, JamesSat, POVACSat, and BrodurSat. So you could look in the little handout I sent you and look at how these numbers change, how thick that red zone is. Okay? Well, golly, that was fast. It's taken me about 7 minutes. Sorry it was so long, but this is some pretty awesome advanced astrodynamics. And I thought you should know this is how we figure out how high to take a pooped out GEO satellite to get it out of the way, free of the GEO protected zone, and not sneaking into the protected zone due to the orbit perturbation effects on the GEO satellite. Thank you. I hope this made sense. God bless you and be safe and stay awesome. Jack signing off.